Hello and welcome to this webinar on tent cables and grid shells, or form finding with GSA. So, form finding, geometric optimization, what's it all about? The architects say form follows function, but as engineers really know, form follows force. So, simple example, steel beam. Majority of steel building structures, you've got to have a horizontal top floor, you've got top flange, you've got to support the floor and everything. There's not much scope in these sort of structures for maximising structural efficiency, other than maybe choosing a lighter beam or maybe going for a few other minor tweaks that you can do like that. We go into some other structures like roofs or long span structures and so on, then there's a lot more opportunity and necessity indeed for making things elegant, lightweight and efficient. I mean, this is an example of a fabric roof from the Eden project down in Cornwall. Columns. I mean, columns just go straight up and down. Not much you can do with those. Well, actually there is. Here is the crypt from the Colonia Güell church in Barcelona, designed by the master Antonio Gaudi, architect and engineer together. He used a lot of form finding to maximise the structural efficiency of his buildings. I mean, his sketches famous Sagrada Familia and also the Colonia Güell. I hope that's pronounced correctly. The Spanish speakers out there will be cringing at the moment, and I apologise for that. He didn't he didn't have computers. He had to use hanging chain models. And if he was around today designing these structures, obviously he could use GSA to achieve the same results. And what a result there was! This is a photograph from the Sagrada Familia Cathedral. Optimized, elegant, interesting, and no vertical columns in there, and likewise avoiding the need for all the flying buttresses you need on your typical Gothic cathedral. Another example of an optimized structure. This is a tension structure, the Marseillaise from Anish Kapoor from the Tate Modern. As you can see, two end support rings, and a fabric structure, and then a weighted ring in the middle to hold everything down. Another example of a geometric optimization. This is the cement hall from National Exhibition in Zurich in 1939, designed by Robert Maillart. I'm not sure the exact dimensions, but you can see it's probably about 20 meters tall from the scale of the man. You can see down here, and it's probably a couple of inches thick. But anyway, considering this is designed by hand, it's quite an amazing structure. So within GSA we use a solver called GS Relax. Those who've been around a bit will remember GS Relax in its sort of previous standalone firm called Fablon. That's now fully, and has been for a while, fully integrated with GSA. It used a method called dynamic relaxation, well, you can use this for geometric and material non-linearity, non-linear buckling, and form finding, which is what we're concentrating on today. What is dynamic relaxation? Essentially, it makes the model go dynamic. Quite literally, the whole structure starts vibrating around with the stiffnesses and masses coming from the structure, and you have these unbalanced positions where there is sort of a resultant force on the structure, which then accelerates things. But what we're looking for is the equilibrium positions where there's no out of balance forces, and so this is what we call convergence, where we get to this convergence. Now, obviously, it's a dynamic way of working, and so you've got to include damping in there to to ensure that the model sort of converges onto the equilibrium position. GSA handles this automatically, with setting the damping proportional to the speed of the elements moving around, but you can go in and take control if necessary. Now, this is not a matrix method, which you can find for normal static analyses, which means you can use this for quite a range of more interesting structures. For example, these two examples here, a 3-pin beam and a pinned cantilever. Neither of these work, obviously, for a linear analysis or a matrix, but with the nonlinear dynamic relaxation in GSA, you can use GSA to solve these sorts of problems. So a quick summary there. GSA automatically deals with non-linear geometric non-linear effects. There's no particular restriction on the type of structure. You can use this from very rigid to very flexible structures, and you can deal with a range of non-linear behaviors all in the one model. Material non-linearity, example, tension only and compression only structures. This is a little tensegrity model. So tension first. Tension structures tend to be quite lightweight, and they resist loads not through their own stiffness, but through the form, the pre-stress in the elements, and large deflections. The pre-stress part is pretty important in these tension structures, especially doing fabrics, because fabrics the pre-stress determines the final form, and you've got to get if you change the pre-stress, the form changes, and so on. And form finding is all part of that. Likewise, you can deal with compression-only structures. This is from the Expo 92 in Seville, the Pavilion of the Future, featuring some dry bonded stone blocks. So that these are just stone blocks placed straight onto each other with no mortar, but then held together by the pre-stress from those steel cables. Now, geometric non-linearity, this will also involve changing load paths. Now, as you change the load on this sort of arch structure, the geometry changes, and so the load path changes as well. You can deal with all these sort of structures in GSA. So, form finding, how to go about it. Now, in GSA we have 3 different types of form finding: soap film, force density, and normal properties. The form finding is important for these sort of structures, because, well, okay, the picture on the left is under construction, but if you get the cutting patterns and so on wrong, or if you get the shape wrong, or you get the pre-stress wrong on these structures, you don't get the nice smooth surfaces that you see on the right. You'll get wrinkles and so on. If you get it right, it looks good. Another important thing, doing something like this where you have the cable nets supporting the arches and the arches supporting the cable nets. Those arches are quite slender. If the forces get out of balance on those arches, the arches will buckle. Excuse me. With the form finding helps you to find the balance structures. So, soap film first of all. Soap film is literally a mathematical equivalent of a soap film, and soap films will try to find the minimum surface area or energy, and the GSA's routines mimic that. Note, being a soap film, you've got to have edge elements to stop the bubble from bursting, and so the 2D elements, they will simulate a soap film, which is a constant stress but 0 stiffness. And you can think of the 1D elements as having constant tension and 0 stiffness, a bit like some elastic band type things. Note that you will have to keep control of the structure when they're exhibiting 0 stiffness, and we have to use spacers for this. I'll come back to those in a moment. Shape is important for these fabric structures, and you typically will be looking for a double curved surface to achieve the stiffness. Three basic forms: of conic, the barrel vault, and the high par. Just about all fabric structures are sort of variations on these three shapes. Edge conditions, you typically either got a fixed edge, such as on the left with the steel beam, or a flexible edge on the right with a cable. You model both of these in GSA. Stiffness themselves mentioned. Under the soap film, the stress is constant, the stiffness is 0, the nodes are therefore free to move around, and so we need to use spaces in the model to control how the nodes are spaced apart. Now these spaces are special elements. See the top example there. A number of spacer elements of the same property go together to make one spacer. You can't have any breaks in the spacer. You can't have any forks or bifurcations. So you'll tend to end up with quite a few spacer properties in the model. End result: high pass structures, saddle structures, and so on. You can also use pre-stress or pressures within the form binding. For example, if you're doing an ETFE foil bubble cladding, you include a pressure in the form finding, and you then get the initial the initial shape. One famous example of this is the water cube bubbles. Water cube structure itself, designed by Arup. The water cube cladding, designed by David Dexter Associates. And because the larger panels, to get them to the required pressure, were going to be yielding too much, they had to preform the ETFE foil, because you can just about make out the strips in the foil, and they used GSA to find the initial shape, pressurize them up, and then you can then use the wind and snow loads and so on these claddings. End results, well, you see it's 1/8 major awards. But you can also use this pressure method for form finding domes and grid shells if you wish. Another basic structure type, the conic. These conics tend to need higher radial pre-stress to avoid necking. That is the fabric sort of touching in the middle. And you note as well that the top is not a point, but it's a ring structure. You can't actually go right to a point. Here's an example of our customers. It's actually sort of more of an art exhibition. It's the New York Museum of Modern Art Liquid Skies exhibition, and you can see the mylar fabric, obviously quite low tension, the edge cables, and it's so lightweight it's apparently been held down by a toddler. So, summing up on the soap film, you've got to use spacer elements to control the nodes within the surface during the form finding. And the soap film, you'll define the pre-stresses in the elements, whether the edge elements or in the soap film itself. And you notice well there that the soap film, you can have different pre-stresses in the various directions. So, demonstration. Let's have a look at this in action. Alright, fire up GSA, and I am going to create a new model, and because I'm using the soap film, I'm going to use the wizard, because that will set up the spaces for me. And 5 meters square, 10 elements, so I'm looking at half meter square elements. You might want to go a bit finer density than this. The property is going to be a fabric, and I will need to set up a material for this. Obviously can't use steel. I'll need to include spaces for form finding. We've got the internal spaces, these are geodesic, so these spaces will ensure that nodes remain on the surface of the fabric, whereas the edge elements, these are free to move around as they feel necessary. I'll have edge elements which I'll put in as ties, and the edge will be the edge tie, and we'll use a 10mm cable for this. Wonderful. So this is our basic model, and as you ask, there are some red dots around the edge. These are coincident elements, which is fine, because what we have around the edge is both the edge cable plus the spacers to control how those cables work during the form finding. So, note on, I am going to take these two corners there, and I am going to pin those, and I am going to switch on my grid in a minute, and I'm going to draw in a couple more backstays. Notice I'll change to property number 2. Wonderful, let's look in the other direction and switch that grid off a minute. And so I'll take those 2 points and I'm going to pin those down at the moment. By the way, if you feel like I'm going too quickly, this is being recorded at the moment and will be uploaded onto the website after the webinar, so you'll be able to follow this within a little bit more, at your own speed. These 2 points here, I'm going to move these two up by 2 meters, and I'm also going to modify those so that they are restrained in the Z direction. So to begin with, they can, during the form finding anyway, they can only move horizontally, they can't move vertically. I will also add some columns in, extrude 1 increment minus 2 meters, and include beams in there, and I'll pick these 2 nodes here and modify those and pin them with a torsional restraint. Wonderful. So that's the basic geometry set up. We also need to set up material, so our fabric material. I'm going to use defined material, and I'm going to say it's going to be a fabric. And for these warp and weft factors and so on, speak to your fabric manufacturer. These are just some defaults. And the properties themselves, still 2D element properties, I'll need them to use this fabric material. And because the fabric elements have no thickness, they have no bending capacity, they have no compression capacity, and so on, I will need to add in, then because they have no thickness, they have no self-weight, and so I'll add in a little bit of mass in there for their self-weight. Let's call it okay. We'll need some loads. I'll go to my gravity loads. This calculates the self-weight of everything, and let's give things some titles. Dead. So that's my dead weight. We can use this self-weight as in the form finding. Not to have much effect on this, it's quite a lightweight structure. So form finding properties now. The soap film 1D properties. Now these will match up with the section properties. Now we haven't defined these yet. Let's take this 10mm cable, copy that down to there, and that is going to be my backstay. And I also want, so those are our 2 backstays there, and the third one is going to be my strut, and I'll use a catalogue hollow section, let's say about 100mm diameter. Okay, so yeah, the 1D soap film properties, row 1 matches up with row 1 here. So this is edge tie, and I'm going to pre-stress, target pre-stress of 10 kilonewtons, and the backstay I'm targeting 20 kilonewtons pre-stress. And so the form finder will try to find the geometry where these pre-stresses are achieved. In the soap film, for the time being, I'll just ask for a constant pre-stress in the two directions. Alright, now then, I think if I remember correctly, I've got enough to set things out. So let's try and analyse this. So form finding. Now, if you can't find these form findings, go to your tools, preferences, advanced features, and make sure that fabric and form finding are switched on here. If you've got asterisks next to them, that means you haven't got a license for them, and come and speak to us and we can see about arranging for you to have a go. So, new analysis task, form finding, using soap film, and I'm going to add in just the dead load in there, so it will take them into account in the form finding. And let's analyze this, and we get a warning to say the geometry will be changed, which is fine. And it's found it. Say modify node coordinates and save the spacer forces and the axial forces as pre-stresses in the structure. So that is exactly what you want. So what we've now got is the found geometry, and you'll see that those columns have angled over. Let's go. They've angled over a little bit, but they're still pretty straight. But we've also now got pre-stressed loads in the edge cables and pre-stress forces in the fabric as well. Right. If we're happy with this pre-stress, let's unshape. Let's apply some other loadings. And so 2D face loads, I'm going to say now property area 1, that's my fabric element, and I haven't created a name for it yet. Let's call it live load. Let's call it, okay, live load. And wind. So we've got a live load on the fabrics, which is going to be in the global direction. It's going to be projected. It's going to be minus 0.6. This is snow load essentially on the fabric. Might not be a problem if we're in warmer climes. And again, for some wind, I'll take a simple uplift case, which is the wind load, which could be a local direction, not projected, uniform, and just one. So, looking at those loads here, if I switch my loadings on, we can see there's our vertical live load, whereas the wind load is normal to the surface. Alright, now we can analyze this. I'm just going to delete out that form finding task, and I'm going to create a new analysis task, which is a static non-linear, and I'm going to add in some locates. Now, because it's non-linear, we have to add the loads into the analysis task, so dead and pre-stress and live, and I'm going to call that dead plus live. Dead plus live, that's better. And also dead plus wind. And if we wish, we can add factors onto here in the analysis. Let's analyze those. Let's switch the loads off a minute so we can see better. So there's the so there's the Nash report. Both have converged. Let's look at the results, and we can see that under the wind we have got. Let's look at displacements first of all. Displacement of about 400 millimeters under wind, and about 225 under the snow load. Now, if you're worried about ponding on the structure, I can look at the global results, the deformed elevation. Or let me switch off the spaces. PG1 to PG start. If you worry about the risk of ponding, if there was ponding occurring, you would get sort of an island of contour in here in the middle, and you then got ponding to deal with. Apart from that, you can also get axial forces in the cables and beams, and I've just realised I've left the Z restraint on those columns, and also projected forces, the axial forces in the 2D elements as well. So that's the fabric analysis. Right. The other form finding method you often find in a number of places is called the force density method. Now, with the force densities, force density is the typical method you use for cable nets. You can also use it for fabrics as well. It has the advantage that it's a simpler method than soap film, though it's not quite so. It's not as good, but it's simpler to use. It's simpler because it involves no spaces at all. So when you're dealing with form find methods where you just define the geometry and you get the shape, it's probably force density you're looking at. But whilst in soap film you're defining the pre-stress, the forces you're looking for, with force density you're defining the force density. It's the stress proportional to the length of the element or in proportion to the area of the element. So for example, if we have this top example here with a different force density in each of these elements, you'll find that they have end up with different lengths at the end. Likewise, you have a longer element, you have a higher pre-stress, and so on. But it still does work. But the results aren't quite as predictable. So, cable net structure like this here, for example, you can get the end results. Summary on this: don't need to worry about spacers. Again, define the edge cable pre-stress force densities and the force density in the fabrics as well. So let's look at this in action. Right, I'm going to create a new model. I'm just going to create a blank model, and I am going to add in, set my default to tie, and so add in a 10-meter long element, which I am going to, let me switch that off for a minute, break up into 1 meter pieces, and I am going to copy that up by 2 meters. Let's look on elevation, and so that top element I'm going to change into property number 2, and we can see this if I switch the colour by property on, and I need some diagonals in there, so I'll set default property number 3, so when I draw these in, they go in, right. Okay, and let's copy all of those 2 meters in the Y direction, and then I'll zigzag at the bottom, which I'll set to property number 4. And so I can see it easier, I will use a volume and just draw them in here. So this is where some hold music would be useful. Only take a moment. Oops. Okay, let's switch everything back on again. This kind of perspective might be, yeah, I guess better. We also need some support points. Those M1s there, those M1s there. Modify these and pin them. Okay, and we need to set up some section properties. Now we've got 4 section properties in here. I'll put them all to this 10mm cable, and I'll just copy that description down. I'm not worried about the names, but the bottom one's 1, the top one's 2, the verticals are 3, and the horizontal is 4. So form finding properties, force density 1D. Again, the first one, the bottom cable, I'll set that to 40 kilonewtons per meter. The top cable 10 kilonewtons per meter, and the other ones just 1 kilonewton. These are the diagonals, 3 and 4. Now we do a new analysis task, which is the form finding using force density. I haven't really loads in here. I just take a blank analysis case and analyze that, and there is our end result. And you can see it has form found in quite a nice looking shape. But if we look at the pre-stress forces on here, so bottom cables, you see we have the pre-stress force density of 40, and we've got about 40 kilonewtons pre-stress in those. Top one had 10, and it's 10 to 11, so it's not exactly the same as what we asked for, but we've got a reasonably constant length. The verticals, you see, they're quite short in the middle, so we're getting about, you can read that, 1 kilonewton in the middle. End cables about twice as long, twice as much pre-stress, and the plan ones, again, about 1.34 up to about 2 kilonewtons pre-stress at the end. And then, of course, with this in place, we can now load this and analyze it, and so on. The third method is the normal property, or for form finding. Now, what normal property is it doesn't use these form finding properties, it doesn't use force density or soap film, it uses the element properties themselves. And so differences in element stiffnesses will affect the final shape. And what it does, it creates permanent large-scale deflections based on the applied load. Very good for compression structures, such as these domes here. These are quite regular, obviously. You can also use it for more organic grid shell type structures. This is the Mannheim World Garden Exhibition, and you can see from the inside shot, the structure is quite slim and slender, but it's very stiff under uniform load, but you still need some minimal bending strength for wind and snow. Now, this was designed back in '75, so wasn't designed using GSA. There was no GSA in those days. It was using a hanging chain model, such as used on Antonio or the Sagrada Familia and so on. Obviously, today we could use GSA either using a soap film or all the normal properties for this analysis. Now, normal properties is very good for creating things like shells, shell structures, but also roof lattices as well. So, summary in this: no spacers or form finding properties, you just use the section properties and large loads to achieve a permanent deflection. So let's look at creating a shell structure like this. Now with shells, now the form finding doesn't work directly on shells, so I am going to show you a cheat or workaround, and I'm going to use both beams and shells in this model. So I'm going to create a half meter grid of elements, and I am going to draw in some beams first of all, and I'm going to draw in a quad, which is going to be my shell or concrete surface. So if I just take this little arrangement, I'm going to copy this. This is a half meter, so I'm going to copy it to create about 10 meters square, and likewise select those, copy that, to get my total grid, and I'm going to pin the midpoints, and you can see the no, that one. The tooltip is quite useful because it shows up the coordinates, and then modify it and just pin those in position. I also need to apply loads, so we'll do gravity load, obviously self weight. Well, let's give these some names while we're at it. Dead and alive. Ooh. So we've got dead weight, and we need both beam loads. Now this is a grillage. If I'm applying some snow loads, property beam 1, lowercase 2, uniform, global, projected, and minus next grillage, so just half that load. Whereas on the face loads of 2D elements, I will set this, what should be projected, to minus 0.6. So if we look in elevation, live load there, no dead load yet because we haven't set these section properties. And for the grillage, I'm just going to use a 200 square concrete, which is a nominal section. But for the slab, I am going to use a 50mm thick shell element. Okay, so we've got loadings on there now. Now for the form finding, now because I've got shells and beams in there, the form finding will not work with the shells, so what I'll need to do is leave them out of the analysis. So I'm going to use a stage definition, construction stages or analysis stages. I'm going to form finding, and I'm going to use the property beam 1 and the static and the property area 1. So what this will do, I'll form find using the beams, and the beams will position the plate or the shell elements, and then I'll analyze the shell elements for static load case. So analysis, new analysis task, form finding on the form finding stage, normal properties, or ignoring from properties, and I'll add in my dead and live loads. I'll put a bracket around those, and I'll multiply them by a large negative factor, 2000 in this case. I happen to know because this works. No magnification, analyze that, and it works. So we've got a nice shape. Now I'm not going to save the pre-stresses in this though. So here is my final shape, and you see it's not quite as flat as you might expect. There's a lot of bulges in it, but these bulges are important for generating, giving the right shape. So let's do a static analysis on this now. Let me just delete that form finding. If this hadn't gone up far enough, we could just rerun that form finding and it'll push it up a bit further and further. So let's do a new analysis, which is a static on the static case. Add in, well, let's default low cases because it's a linear analysis, and analyze this, and we find we get a warning which says that too many elements are warped out of plane. Now we can collect these by double clicking on this underlined section. You see that most of them are actually selected. In fact, if I look at the geometry contours, we see that just everything is warped apart from the 4 in the middle. So let's use the sculpt tools to split quads down to tris. And tris, obviously, triangle elements does exist on a plane, so you don't have to have the warping problems. Rerun that analysis, and that's worked. And let's look at the results. So first of all, we can look at displacements. Live load displacement 0.2 millimeters. That should be okay, I should think. Excuse me. But we can also do ULS combinations on these. 1.35, 1.5, and then not look at translations, but moments, which are very small, but in-plane forces are much larger. You see the compression loads down to 150 there. So this is essentially as a compression-only structure, because the shape is right. Alright, and actually to prove this, we can also run, as we were asked earlier, a buckling analysis. So look at modal buckling on the static form. Just take a couple of modes and apply dead and live loads, and we can see how much load we need to apply to buckle this. And well, let's look at the deflected shape, and we can see the load factor here is 11.4, so it would take 11.4 times the applied forces to actually make this shell buckle. And the next factor 23. Bear in mind, of course, obviously the asymmetric loads can govern the design, so you need to check for wind, snow drifting and that sort of thing. Okay, so where next? If you're an Arup user, or you've already external customer with Fabric or Suite licenses, just make sure the form binding is activated in your preferences. If you're an existing GSA user, or you're a non-GSA user, contact us and we can arrange for a 2-week trial license for you to try out for yourself.